Okay, welcome back to First Person Radio, the very low effort YouTube channel, where I try and explain to you the basics of radio communication. Everything you need to know and nothing you don't is the idea. So today we're going to be talking about something that is fairly technical, but I'm trying to cover it in as non-technical of a way as possible and only give you what's necessary. And that topic is HF radio propagation. There are a lot of extremely technical articles written about this, and people can go around and around on the details. But the basics of it are actually fairly simple, and honestly, about all you need to know, at least to get close. So let's get started. HF radio is wonderful because it does not require you to have line of sight to another radio station. VHF and UHF, any radio that's small enough to be held in your hand and carried, with an antenna that's small enough to be held in your hand and carried, is going to be basically line of sight propagation. And if you go beyond a hill, unless there's another piece of equipment relaying your radio signal, it's not going to make contact. The only way to make point-to-point contact with no extra equipment relaying your signal beyond line of sight is high-frequency radio. So let's go over how that happens. We have a couple different radio transmitters here trying to communicate with each other. We're going to say that we're this one right here. And we've got this big hill in the way. So none of these guys are within line of sight distance. What we're trying to do is our radio is sending out radio waves in pretty much all directions. And some of them are going to make it through and some of them won't. And we need to pick a frequency based on the conditions and who we're trying to talk to, such that our signal will be heard by them. A lot of this is kind of unpredictable and varies depending on the day and on the solar cycle, but there are general trends that we can observe. So what's going on here is that there are several different layers of the atmosphere, the ionosphere, actually, the very, very upper layers of the atmosphere next to space that are acting on our radio signals. They're excited by the sun's rays. The sun is kicking off all sorts of stuff. It's kicking off radio waves, it's kicking off visible light, X-rays, gamma rays, all sorts of stuff. And those are hitting the molecules and atoms in the upper atmosphere and exciting them and doing a few things that we can take advantage of. So the two types of layers that we're really concerned about is the D layer, which is a lower layer, and then the E and F layers that for our purposes we're just going to consider, one layer. And they do two different things. The D layer will absorb your radio signal. It'll kind of muffle it, and if it's too low energy, it'll just eat it up completely. The E layer will refract your radio signal, and this is the layer that we really like because if I send a radio signal up here and the conditions are right, the E and F layer will turn it back around and bend it back towards Earth. And that is how we're making contact. So for any given signal that's in the HF spectrum, you're going to have waves sent off in all directions, and they're going to hit the atmosphere at different angles. Now, if we look at the D layer that absorbs our signal and the E and F that refracts it, the higher the energy, the radio wave, the harder it is for the D layer to absorb it. It'll punch through the D layer easier, but also the harder it is for the E and the F layer to refract it. And when I say energy, I'm not talking about how many watts your radio is putting out. I'm talking about what particular frequency of radio waves you're using. Higher frequency radio waves contain more energy per radio wave, if that makes sense, than lower frequencies. So what's going to happen is you're going to send out signals in all directions, and some of them are probably going to go near straight up. Say we're doing this on like the 40-meter band. What's going to happen is some of them are going to come pretty much straight up, and they're going to punch through the D layer no problem because they're coming at a nice steep angle. But the E and the F layer is not going to be strong enough to stop them. They're going to bend a little bit, but they're not going to come back around all the way, and they're going to punch off into space. You're going to have some other waves that are going to go at a real shallow angle. And because they're at a real shallow angle, they're going to spend a lot of time in this D layer. And the more time they spend in the D layer, the more they get absorbed. And they're just going to peter out in the D layer and not go anywhere. But somewhere in there, there's a middle ground where it's steep enough in the D layer that it doesn't spend too much time there and it gets in and out and it doesn't get absorbed. But it's not so high energy that the E and F can't reflect it. And those will come back around and make contact with the folks we're trying to talk to. So you need to pick that middle ground depending on who you're trying to talk to and how far away they are and what the angle is to the atmosphere so that you can make contact. So if I'm trying to talk to this guy out here, I need something that is going to have enough energy to survive that D layer for a long time. And the E and the F layer is probably going to be fine because it's coming in at such a shallow angle, it's a lot easier to refract. So I'm going to use a higher frequency for this guy. For this guy, he's much closer in. And I need something that is going to be easier refracted by the E and the F layer. Something that's a little easier to bend around. And I'm not as concerned about the D layer because I'm kind of coming straight in and out and it's not there as long. So I would use a lower frequency there. So for people who are near to you, you will use a lower frequency, and people who are farther away, you will use a higher frequency. Okay? Now the other thing that's going to affect this, so we have the angle of the radio wave, that's one thing that'll affect it, and the other is the frequency and how much energy that radio wave carries. The other thing that's going to affect this is the solar activity, right? So the more solar activity we have coming in, it makes the E and the F layer more reflective, right? So that's really great for us, but it also makes the D layer larger and much more likely to absorb your radio waves, and that's bad for us, right? So the more solar energy coming in, the higher the frequency we're going to need to use because the D layer is stronger, but also the E and the F layer is stronger, so we can use higher frequencies, right? So we get the most solar energy by far during the day. During the night, you're on the other side of the atmosphere and you don't get hardly any solar energy, and it takes a little while for the atmosphere to kind of settle down, so it doesn't go away completely, but you're going to be using much lower frequencies, right? So during the day, we're going to use a higher frequency. During the night, we're going to use a lower frequency. And these two things are kind of in conflict, right? So your daytime near frequency, which is higher because it's during the day but lower because it's near, might be the same as your nighttime long distance frequency, which is lower because it's night but higher because you're trying to talk further away, right? Those two things, you just got to figure out where you end up at the end of that calculation. All right, so near and far, day and night. The other thing that affects it is the solar cycle and the solar activity, and that's really hard to predict. That is where the unpredictability really comes in, and when people talk about, the band just wasn't good today, that's what they're talking about. Usually there's a frequency that will work. It just might not be the frequency you expect. It might be a little bit higher or lower. So it's a good idea to have, people talk about a PACE plan, a primary, alternate, contingency, and emergency, right? There's only really 4 bands that you'd be really talking about for HF preparedness, but at least a primary and an alternate. And you would want them to be on different bands so that if the conditions are such that one of these bands just isn't working for you today, the other one still gives you a shot. All right, so let's get down to brass tacks and talk about the takeaways from this. So let's talk about a couple of specific frequencies. So the 20 meter band is at 14 megahertz. It is very popular, and during the day, it is a great long haul band. It's got a lot of energy, so even during the day when the D layer is really thick, it's able to get through no problem, and the E and the F layer can reflect it. So it's great for long range during the day. But closer in, it doesn't work, right? Because it's coming at a steep angle, can't be reflected, goes off into space. So this entire region from like here to here, you're not really going to get any real radio contacts if they're not within line of sight if you're using the 20 meter band, and that's called being in the skip zone, right? In the skip zone, you can't make contact because the only radio waves that are coming back down to Earth are going over the heads of the people you're trying to talk to. So 20 meters during the day has a large skip zone. Now at night, E and the F layer is even more is much more fragile, right? It doesn't refract as well, and pretty much everything on the 20 meter band is going to go into space. So it's pretty much useless at night. They'll just say the band is dead, right? The band is there's not a lot of activity. You're not going to hear somebody unless they are within line of sight range of you. So it's basically useless for us. You may as well use your Baofeng on VHF and UHF. So next one is going to be 40 meter band, right? Now during the day, depending on the conditions, if it's a really good day and you're getting really good, like a lot of solar radiation, it might be the perfect band for you, right? So the 40 meter band, at these shallow angles, it doesn't work so well, but you know, a little bit closer, maybe there to there, right? It'll work great. So the 40 meter band can be a good, like a regional band during the day. You might have some skip zone, maybe, depending on the conditions. But on the 40 meter band, you can expect to talk maybe, you know, a couple of states away. I would expect it to be maybe 100 to 600 miles at a guess. Hard to tell. Again, depends on the conditions. And then at night, it acts a lot like the 20 meter band, right? Because now those steep angles aren't as much of a problem because the D layer is mostly gone. So at night, acts like 20 meters. During the day. So long range, large skip zone. Now, let's talk real quickly about NVIS. So you'll hear people talk about NVIS communication, and it's got this kind of aura to it, like it's tactical, and the military uses it, and it's really cool, and what kind of antenna do I need for NVIS? So NVIS stands for Near Vertical Incident Skywave. Near Vertical Incident Skywave. So let's look at this backwards. Skywave means that the radio waves are coming back down from the sky. They're refracting off of the atmosphere. So that's all of what we're doing with HF. Near vertical incident. So the angle of incidence is the angle that the radio wave makes when it hits the atmosphere, right? Shallower angles, easier to reflect, easier to absorb. Steeper angles don't get absorbed, but they don't get reflected. So near vertical incident just means it's going nearly straight up and nearly straight down. So what does that tell us about the frequency we want to use? Nearly straight up and nearly straight down means we want to use a low frequency for near distances, right? So 40 meters can work for NVIS depending on the conditions. So some NVIS. Not always, but sometimes. During the day. At night, you're not going to get any NVIS on 40 meters. It's just going to punch right through. So now let's go to the lowest band, and I'll go to the 60 meter band later. But the lowest band is 80 meters, 3.5 megahertz. It's one of the lowest bands that we'll commonly use. There are other bands below it, but I wouldn't really recommend them if you're getting into prepping. The 160 meter band is about 1.8 megahertz, and you need really big antennas for that one. 80 meters is a large enough antenna. It's already a bit of a pain to manage. But, you know, it can be done. It's about 40 meters of wire. So you put that in a tree, you can make it work. So the 80 meter band during the day doesn't really do very well. Even at those near vertical angles, it can get absorbed pretty heavily. It doesn't really, just doesn't have the energy to work during the day, and you also have a tremendous problem with atmospheric noise. So the 80-meter band is very limited during the day, right? And if you're going to get any good good signals from the 80-meter band during the day, it's probably going to be ground wave, which is a little bit different. We can cover that later. It's a little bit more of a difficult path to go for your radio signal, and it works better when you put out a large amount of power and you have a nice tall vertical antenna. So I don't consider it as practical for the field as Skywave, but we can do a video on ground wave later. So you maybe ground wave, but during the day it's going to be very limited. Now at night 80-meter band really shines. It works fantastic for NVIS at night. And in my experience has been very reliable. So if you had to pick one time a day and one frequency, 80 meters shortly after sunset when you're making camp is not a bad time to try and make contact with your other guys in the area. People are usually not moving around that much after sunset, so it's not like they have to stop and set up the antenna, right? They're usually probably making camp or home, and you get really reliable propagation on the 80-meter band. You're going to have to use a little bit larger of an antenna, but you can make it work. So 60 meters is kind of what I'd like to think of as the Goldilocks band, right? Now, the 40-meter band and 80-meter band, they give you a big chunk of spectrum to use. Like on 40, it's basically 7.0 to 7.3, and on 80, it's like 3.4 to 4.0. They give you a big, wide chunk of spectrum to use. On 60 meters, they give you 5 specific frequencies, 5 channels that you can use, and they're real particular about the type of transmission that you send and exactly how much bandwidth you can use, because they want, you know, those 5 bands are kind of those 5 channels are on some precious spectrum there, and they want to make sure that the amateur radio operators aren't taking up too much of it. Now what that tells me is that this is a really valuable little chunk of spectrum here, and it's probably really useful, right? Because the 60-meter band is great for NVIS during the day. So daytime NVIS. And at night, it still works at night, and it'll reach out pretty far. It's probably going to act a little bit like 40 meters at night, at a guess. I haven't really run 60 meters at night a whole lot. But I would consider it great for the daytime, and you might be able to make it work at night as well. So maybe we'll put this as a maybe. Maybe mid-range. Okay? So generally speaking, during the day, I would say if you're talking to somebody who's close enough to help you, right, not somebody on another continent, I would say 40 or 60 meters are your best bet. 60 is probably a little bit better than 40, but 40 might do it, especially when you have periods of higher solar activity, which we're actually in a period of high solar activity right now as of 2024. Now, at night, I'd say 80 meters should probably be your go-to, and maybe try 60 if 80 isn't working. So, as a rule, I would stay within these 3. The top 2 during the day, the bottom 2 during the night. So let's talk a little bit more about NVIS and the types of antennas. People will talk about using particular NVIS antennas. You don't really need to worry about it that much. Just get a wire in the air, something resonant on the frequency you're using. As a rule of thumb, so the lower the frequency, the longer the wavelength, and the longer the antenna needs to be considered a full-length antenna. Your full-length antennas are going to be 1/2 wavelength. Full-size antennas are 1/2 wavelength, and wavelength is often represented with lambda. I'm just going to use this as an abbreviation. Or, you know, you can do kind of a half size, 1/4 wavelength antenna that's still kind of considered a full size. Like your antennas on your Baofeng or something are going to be a 1/4 wave vertical. But a half wave is a proper full-size antenna. A dipole is 2 quarter waves, a positive and a negative, and it's a half wave long, right? So on the 80 meter band, it's called the 80 meter band because one full wavelength is 80 meters long. So a half wave antenna is 40 meters. It's a lot of wire, but it's not so much that it's impossible to carry around. And all you got to do is get it in a tree, mostly horizontally, and a little bit off the ground. Some things about NVIS antennas, they work better when they're horizontally oriented, right? Because a straight up vertical antenna like this kind of puts a lot of radio waves kind of out this way, but it actually has a null, a point where it doesn't put very much radio signal directly in line with that antenna. So if I've got an antenna pointing straight up, it doesn't put a lot of energy straight up, which means that I don't have a lot of energy coming right back down near where I'm at. So even here, I might not get a whole lot. So you don't want a vertical. You want an antenna that kind of comes out like I like to use an inverted V antenna. So say this is like a tree branch we're looking head on, and this is the ground. My antenna comes up over the tree branch and then comes back down on the other side. And that works great, and it puts a lot of energy upwards, right? And the other thing that helps with NVIS antennas is if they're a little bit lower to the ground, which is great for us because if we're operating portable or trying to operate low visibility and we don't want to erect a huge radio tower, we like our antennas to be fairly low to the ground. I think the rule of thumb was 1/4 wavelength off the ground, or maybe even less, maybe to 1/8 of a wavelength. So that's, 10 meters, that's 30 feet, and that's very doable. So low to the ground, a horizontal wire, you're good to go. And that's actually pretty easy to do. And even on the 40 meter band, it's only going to be 20 meters long. It's even easier as you get higher in frequency. All right, so I think I covered everything I wanted to. Let me know if you have any questions or if any of this was clear as mud, because it probably is just a little bit. But I hope it was helpful, and I hope it'll give you a basic understanding of what HF frequency to choose, depending on who you're trying to communicate with.